there are still people doing heavy fermions in the world. It's not very popular at the funding agencies, but there's still people out there. So this is today's lecture, the 6th lecture. Thank you all for coming, all 7 of you. And Antonio Castroneto wanted some emphasis on 2D because, of course, he runs the Center for Advanced 2D Materials, so we'll talk a little bit about 2D. He has a broader perspective on two-dimensionality and heavy fermions. So first of all, you might ask, what does heavy fermion mean? Well, heavy fermion was a term invented by a German who did not speak English when he was born. And so you might think, is he talking about muons? A muon has a rest mass of like 100 times the rest mass of an electron, so you might think that he's talking about heavy muons. What he's talking about is he's talking about high effective mass electrons. And rather than calling them heavy electrons, he decided to be fancy and call them heavy fermions. And everyone since then has been forced to use the same term, but of course there are a lot of fermions that aren't running around in lattices carrying a current. So that's where the name comes from. And how big the effective mass of the conduction electrons has to be is a matter of definition. And we know that the specific heat gamma is proportional to the electronic density of states. And so that's where we get the effective mass from. So why are heavy fermions interesting? Well, if none of them were superconducting, they wouldn't be. So we'll mostly focus on the superconductivity. Talk about the history here. For those of you going to make a discovery in your lives that's not in agreement with accepted belief, you may have trouble getting people to believe it. Certainly Steglich, who discovered the first one, had trouble getting people to believe in that this was a superconductor. They thought it was something else. And then after this discovery in 1979, the next heavy fermion superconductor discovered was 4 years later, which is quite a while. And this was actually discovered in 1975. So I worked for the guy that discovered it in 1975, Ernst Bucher, later in 1976, so sort of a year after he discovered it. And what he did was he discovered magnetic susceptibility measurements that said that it was a superconductor at 0.9 Kelvin. So normally, when you have a minority phase in a material, and you're pretty sure that the bulk of the material is not superconducting, and you're measuring the magnetic susceptibility, normally what you do is you grind it up. Because if you take a two-dimensional sheath on some grain surface and you grind it up, then you break the sheath and it no longer gives shielding in the magnetic susceptibility measurements. And so the signal will go down. So Bucher ground up his sample of uranium beryllium-13, and the susceptibility still showed superconductivity. He ground it up some more, it still showed superconductivity. Unfortunately for him, he did not have a bulk measurement at 0.9. He didn't measure specific heat that low, so he never saw it. But he told everyone that would listen, this is a very interesting material. And later Bucher went to Switzerland, and he was running around ETH in Zurich, and he told Hans Ott, this is a very interesting material, you should look at it. So Hans Ott had the sample made up, measured the specific heat, and published heavy fermion superconductivity, essentially based on 8-year-old data. Okay, so this is not necessarily all that hard discovery, but still, it's 4 years later. And then we at Los Alamos found this one another year later, and you might ask, how is it you found superconductivity here? Why is it you were looking? We weren't. It's an accident. What had happened was I was interested in the specific heat because it showed paramagnon behavior. We'll talk about that. Zach Fisk was interested in it because he made some nice crystals, and we'll talk about that. And Zachary's favorite measurement method was the resistivity, and he always wanted to know the room temperature value divided by the T equals 0 value. He always wanted to know that ratio. And so he gave some samples to somebody to go measure in a dilution refrigerator. The first time they measured it, a lead fell off and they couldn't get the data. Second time they measured it, he comes down to our offices Friday afternoon and says, it's superconducting. So in 3 weeks, we sent it off to FSBAR loaders. I mean, we just jumped on it. He was cycling his dilution refrigerator in a 12-hour span, and it was an old Janus fridge. He worked like a dog, the guy running this fridge. We got the specific heat, we got the resistivity, we got the susceptibility, and we published in 3 weeks. So that was a very quick result. So why are they interesting? Superconductivity. What did the heavy fermions in 2D tell us? That's for the end of the talk. Okay. So Stewart had trouble making this material in a bulk superconductor, and we all know the trick today. If you want to make this material have a bulk TC, you have to have extra copper. So if you make cerium copper 2.2 silicon 2, you'll get a nice transition. If you make copper 2, you won't. You'll be in the wrong part of the phase diagram because there's anti-ferromagnetism running around in this phase diagram. So it took him a whole year. And I heard a German colleague, who will remain nameless, call Stewart a blockhead, as in stubborn. Well, stubbornness paid off. Okay? So this is a quote from his paper, and what it shows is that superconductivity is present in the same electrons that have strong many-body interactions, which was a first. Okay? And the specific heat, gamma, the C over T term, is proportional to the density of states. The Fermi energy times 1 plus lambda, where lambda is the normalization factor. And that's where this came from. So here's specific heat divided by temperature. Here's an extrapolation to T equals 0. Here are these enormous, enormous jumps. Notice that we're using joules per mole here. We're not talking millijoules like we've always been talking about before. These are joules. This is a gamma of 1,000 millijoules. Okay? And if you look at a normal non-heavy fermion like vanadium-3 silicon, which we've talked about before, TC of around 17, the gamma is 60 millijoules. Okay, so this is a much different sized gamma and a much different sized delta C over T. So we'll go back to this. So the point here is if you have a large delta C over TC, then you know that this large delta C over TC is due to a large gamma, because remember, delta C over gamma TC, BCS is 1.43, unconventional superconductors, maybe it's 1.1, maybe it's 2, but it's somewhere proportional. So if you have a huge delta C over TC, then you have to have a huge renormalized density of states, highly correlated electrons, causing the superconducting jump, okay? Because this is opening up the gap in the superconductor. This is directly related to the superconductivity, this jump, okay? So, joules, not millijoules. Okay. Stewart had a hard time getting it by the referees. The referees insisted that he show flux expulsion. Everyone else, when you publish the superconductor, you say, look, the resistance goes to 0. People say, it's a superconductor. If you're really being careful, you say, look, there's a jump in the specific heat. Referees say, oh, it's a superconductor. Stewart said that And the referee said, it's an accident. There's a second phase that goes superconducting, coincidentally, at the same place where there's a jump in the specific heat. But the jump in the specific heat, this is some other physics. This is some magnetic transition. There's nothing to do with superconductivity. So Steglich had to show flux expulsion. And as soon as you show flux expulsion, then it's a bulk superconductor. He was the only heavy fermion superconductor discoverer that showed this. The referee told us when we sent in uranium platinum-3 that we should do the Meissner effect, and held up the publication of the paper after we wrote it in, took the data and wrote it in 3 weeks, held it up for 4 months. And we appealed to the editor. So if you have a paper rejected that you're pretty sure is right, just say, I appeal to the editor. The editor looked at the paper and said, looks good to me, published it. It was the second most highly cited paper in its year. Like 150 sites. Okay, so it's one of these citation index famous papers. It started a whole field. So there's Hans Ott and his uranium-13. There's us and our uranium platinum-3. And just, if anyone's ever seen an American penny, they're like a 5-cent coin in Singapore in size. And this is how big Fisk's crystals were. They were grown in a bismuth metal flux. You then dissolve the bismuth. And essentially when I asked him for some sample, he said, here's the crucible in which they sit. You go find some. So I found something like 14 milligrams. All of these crystals together weighed 14 milligrams. I glued them down on a sapphire disc and we measured the specific heat. The neat thing about these is this is an hexagonal structure and the C-axis is along the needle. And if you look at the needle endwise, you can see, in some of them, you can see 6 faces. So the crystal habit, or the physical outer appearance of the crystals is really quite perfect. So just to remind you, part of my job as a lecturer is to make sure you guys connect all of this. We've already seen the heavy fermions on this graph before when we were talking about transition temperature and the characteristic energy of the spin fluctuations. And so we spent our time discussing this region, but this correlation started off with the heavy fermions. Here's uranium platinum-3, uranium beryllium-13, cerium copper-2, silicon-2, and some other superconductors, 1 or 2 of which we'll discuss. So you've seen this before. All of this fits in the same picture. So I mentioned last time that one of the exciting things about uranium platinum-3 is it's not S-wave, for sure. It's not D-wave. It's in fact F-wave. So it has nodes all over the Fermi surface due to these lobes of the energy gap at the Fermi surface. So it's F-wave. It's the only one known as far as I know. So for those of you who are experimentalists, how many experimentalists do I have? Oh, what a minority. Anyway, if you're worried about how to measure these things, measuring cerium to low temperature and finding the superconductivity at 0.6 Kelvin is no problem. Measuring uranium beryllium-13 or uranium platinum-3, you have to worry about the cooling power because the uranium is radioactive and creates a self-heat. This is a ball of plutonium measured with infrared sensitive film, and it's just glowing from its own self-heat because it decays at a sufficiently fast rate, 24,000 years is the half-life of plutonium-239, that it's warm. And so when you measure uranium-containing samples, it's hard to get below 80 millikelvin. It's hard. And it has a difference in temperature between the sample and the surroundings due to the radioactive heat. The largest example I know about is when I measured 5 milligrams of 243 americium, which has a half-life of only 7,000 years, the self-heat on the sample was 34 microwatts. So it was in there radiating all over everywhere. I'd already had children, so that was okay. But it was pretty radioactive. The thing that I didn't know about samples that are that radioactive is when they decay, it's not a gentle process. So what I did was I had a pan balance where I was measuring the mass of the sample. I had a sapphire disc that I put the sample on, and then I had my piece of americium right there. I measured the mass of the sapphire disc, I measured the total mass with the sample on it, and I said, okay. And just to be careful, when I took the sapphire disc off, I checked the pan balance to make sure that I hadn't contaminated it. It was hotter than a $6 pistol. What happens in a sample that's radioactive is when it decays, let's say this is the americium, it's not gentle. It's not, here's an alpha particle, here's an alpha particle. When it decays, it blows pieces of the sample off. And so a chunk of the sample, along with the creation of the alpha particle, which is helium gas, gets blown off the sample. The piece lands here, so let's suppose this is the sapphire disc. This then decays, and it jumps, and it jumps. And within the 5 minutes that I was on the pan balance, some of the pieces had jumped off the sapphire disc and onto the pan balance. And the person that owned the pan balance was not terribly happy with me, because I had turned his pan balance into a source of americium-243 in small amounts. So we cleaned it up. But when you work with something that's this radioactive, there's a whole another set of conditions that you have to live with. So again, what you're trying to do is you're trying to measure C over T as T goes to 0. Americium is interesting. I know that you guys won't take this home and tell your wives and friends and children, wow, americium's a superconductor. Man, that's interesting. It's an elemental superconductor. It belongs in a table somewhere, 0.7 Kelvin. But anyway, we wanted to know what the specific heat gamma was. And so these are the data. I measured the data. He put his name first. Never mind. We'll talk about that sometime. But I could only get data down to a little over 7 Kelvin because of the self-heating. And so I had to extrapolate the gamma to low temperatures. Obviously, the fiddling with the getting the slides on the screen today has moved this. But anyway, this is an extrapolation of gamma, and it goes down here to 2 plus or minus 2. So the gamma is an uncertain number, and it's because the data are from a fairly high temperature. So another thing you can do when you're looking at, here's another one of the heavy fermion superconductors, is in addition to their superconductivity, they also have magnetic transitions that can be influenced by high magnetic fields. So if you look at the magnetization versus, this is 40 Tesla, some Japanese data from Takoichi, you can see there's something happening in the C-axis direction in the magnetization. So this is just a straight line trying to show you that there's a straight line behavior here, but it looks like there's some sort of curvature, and then there's some sort of rise starting up here at 48 Tesla. So we went and measured the specific heat. So there is a field-induced transition in high magnetic fields. These are data, the highest field data almost that I ever took, up in the hybrid magnet in Tallahassee. And you can see that we needed 48 Tesla because the transition was still developing as the field went up. So when you consider superconductivity at low fields, you also have to consider that there are magnetic interactions that you might learn something about at high fields. Uranium, ruthenium-2, silicon-2 has a lot of transitions going on in its magnetization. It has 3. And if you look at the specific heat at the critical field, of this transition at 17 Kelvin, you can see that there's another transition at high field centered around 38 Tesla there. So we talked a few times about how to determine nodes, and we said that Bolovic had a theory that said if you measured the specific heat like Cam Moeller did as a function in the superconducting state, as a function of field, that it went as the square root of h. What I didn't tell you is if you throw in defects, you can wash this out so that it looks like h times the log of h. And of course, if it's just linear, it's just a normal BCS nodeless superconductor. But what I wanted to spend a second on was, again, this has been messed up by our fiddling with the dimensions. The temperature dependence makes a difference, and sometimes you have to go to low temperature, 100 millikelvin, to find out what temperature dependence it is you've got. And so here's an example with one of these heavy fermion systems that down here at low temperatures you can tell that it's more of a log temperature dependence than it is a power law temperature dependence, t to the exponent 1 minus lambda. This lambda should be up here, sorry about that. And there are other temperature dependences, not just log T, not just T squared log T, which uranium platinum 3 has. This is actually why I was interested. This is paramagnons. Here's a fit to some data from uranium to cobalt to tin, which is another heavy fermion system with a C over T at low temperature of over 300. And you see that the paramagnon fit doesn't fit at all, nor does the log T fit. It's a curve against log T. But what does fit is square root of T. So there's a bunch of temperature dependences out there running around trying to confuse you. Now we're back to the heavy fermion superconductivity, which was the topic of the lecture. It turns out that Hansat measured pure uranium beryllium-13, published it, and says, okay, I'm happy. And Jim Smith said, I'm not happy. I'm going to put everything I can think of into this structure and see what happens. And what Smith found was he found when he measured the magnetic susceptibility, these are specific heat answers coming out of seeing where that peak is. But if I just take the susceptibility, what Smith found is when he doped uranium beryllium-13 with thorium, and it goes in perfectly because the endpoint exists in the same structure. Thorium beryllium-13 exists in the same structure as uranium beryllium-13. So you can put any amount of thorium in you want and get a single phase material. What Smith discovered is his AC susceptibility had this really funny behavior. It turned flat between 2 and 4%. So he's doping in thorium, Tc goes down. He's doping in thorium, Tc stays constant. He's doping in thorium, Tc stays constant. So he says, I bet there's some interesting physics there. And he gave some samples to Hansat to measure the specific heat, and this shows up. So there are two transitions, and you can argue about one being S-wave and one being D-wave. The theorists have had a good time with this. You can argue about lots of things, but it's something you need to prove that this is superconductivity. This sees a Meissner effect. This sees resistive transition go to 0. And this temperature also sees a magnetic susceptibility that says it's diamagnetic. But when you get to here, the resistivity is already 0. So you can't measure the resistivity down at 0.4 Kelvin and see a second transition. 0 is 0. It's been shorted out. The specific heat has a transition, but how do I know that's superconductivity? It's a jump. It's just like the original cerium copper 2 silicon 2 and the referees. They said, well, you've got a jump, but how do we know that's a superconductor? And there's the shielding has already taken place. But what you can do is you can look at the field in which field first enters in. You can look at HC1, and you can look at HC1 as you lower the temperature, and the slope of the rise of HC1 with temperature changes here, implying that there's a change in the superconducting density of states. So you can actually prove this is a superconductor, and there are, of course, other measurements, but that was the first one. So this is a very interesting phase diagram. This was my postdoc in Germany when I was there. We did a lot of measurements, and we had interesting results that sort of talked to the unconventional superconductivity down here. And we disproved a lot of theories. We always enjoyed that, for you majority of theorists in the audience. So anyway, there are a lot of heavy fermions that aren't superconductors. One of them is plutonium-aluminum-2. Here's the resistivity. Everybody can see there's something going on at 8 Kelvin. Al Arco was the one that discovered that. Once you leave the sample sitting around for 3 months without annealing it, the damage due to the radioactivity destroys the resistivity transition, and the resistivity comes up here and goes flat. It does not fall. So when you're dealing with radioactive samples, you have to worry about how old they are. How long ago was it made? Because if it was made 3 months ago, the properties are different than if it was made yesterday. Or you can anneal it. So we went in and did specific heat on a fresh sample, and we found that there's a peak in the specific heat at around 8 Kelvin, which has relatively no magnetic field dependence. So we think this is a structural transition. We've tried to get neutron scattering people to go look for the structural transition. They've never done it. And of course, what the resistivity can't show is down at lower temperature, there's something else going on. And this, we believe, is anti-ferromagnetism. So again, this is a heavy fermion system. If you talk about the gamma as being something like 270, but it's not superconducting. Okay. Professor Castaneda would like you all to learn about two-dimensional behavior. This is a short course in two-dimensional behavior that should have 3 lectures devoted to it. So you have to pay really close attention. Okay, so what we're talking about is we're taking a bulk heavy fermion system and we're making it thin. So we're using MBE, so we've got really clean samples. We're using cerium indium-3 layers in between lanthanum indium-3, which, as Matthias would say, is a vegetable, doesn't have any activity going on. And just be aware that this isn't all that heavy. The gamma is only 120 millijoule, and it's also an antiferromagnet. So things to worry about. So here is a cartoon picture of what it might look like. The red layers every 4. So here's a cerium indium-3, then 1, 2, 3 lanthanum indium-3s, then another cerium indium-3. The red ones are the cerium indium-3, and the yellow ones are the lanthanum indium-3. And if you wanted to look at a close-up, here it is, cerium indium-3, lanthanum indium-3, and a scale of 2 nanometers. So, okay. There's a lot to learn here. First of all, I'm hiding this from you. I have not labeled this axis yet. Don't worry about this axis. We're not there yet. We're over here on this axis. We're over looking at the red points. This is the Néel temperature. M is the number of the cerium indium-3 layers in between the 3 lanthanum indium-3 layers. So if I go to a big number, so more or less, so I got bulk cerium indium-3, then of course the antiferromagnetic transition is where we think it is. It's up around 10.2 Kelvin. As I make the number of layers, say, more like 3, you can see that the Néel temperature has dropped down here to a much lower temperature. And if I make the number of layers only 2, I get rid of correlations that are leading to the long-range antiferromagnetism, and my T-Néel drops to 0. So, haven't talked about the blue, haven't talked about this axis. I'm just doing what happens when I layer cerium indium-3 with something that doesn't have any activity but has the same structure, so I can do epitaxy. And this is what happens. 1 over the number of layers that are in between the lanthanum indium-3, T-Néel does this. So one of the things you can do with dimensionality is you can tune your physics. You can tune your superconductivity. We'll talk about that next time. You can tune your normal state properties, anti-ferromagnetism. You can tune things. I have a colleague down the hall, Art Hubbard, who built a new rig where he could make two-dimensional films, and he was discovering all kinds of things. What happens when you make iron thin? He was just doing all kinds of things. You have to do it cleanly, or you're looking at some secondary effect. This is MBE, this is clean. So, okay. So what happens when a second order phase transition gets suppressed to T equals 0? Well, what that causes is quantum critical behavior and non-Fermi liquid behavior. We are now going to do, in 5 minutes or so, a very quick short course on quantum critical behavior. Okay? And we've seen a little hint of this already, but we'll remind you of it. A quantum critical point, and this is something people in the literature, when this field first started in the early 90s, when this field first started, people didn't really understand that you can suppress the second order phase transition to T equals 0, and you might not have any fluctuations left over. You might have suppressed everything, and you might not have a quantum critical point. So you have to go look, and we'll talk about that. So if there is a quantum critical point, then the neat thing is there are quantum fluctuations at T equals 0, unlike a classical transition at finite temperature where you have classical fluctuations above the ordering temperature. If you suppress the second order, not first order, not ferromagnetism, if you suppress the second order phase transition, superconductivity also works, second order phase transition to T equals 0, exactly at that point in the phase diagram, there is a huge effect at finite temperatures because the fluctuations become infinite in extent. You can have a quantum critical fluctuation in a phase diagram and evidence of those fluctuations at 10 Kelvin. It's an enormous difference between a few millikelvin and 10 Kelvin. So there's a lot of interest in quantum critical points, also because they affect superconductivity, which is the reason it's in this talk. So anyway, it can occur when you suppress, and again, we've changed the size of the slide, but anyway, remember what a Fermi liquid is. It has rho naught plus a t squared. Please remember in your mind that that's t squared. So Fermi liquid is resistivity goes as t squared. If it's non-Fermi liquid, that just means it's not t squared, so it's something else. And theories will tell you whether it's 1 or 1.1 or 2/3. So you can tell from the temperature dependence of the resistivity what's going on in your physics at the quantum critical point. So now I have revealed the right-hand axis. And what was that? Well, that was the coefficient A in rho equal rho naught plus AT squared. So this says that the blue points are in a region where I have Fermi liquid behavior because I have T squared. And if I follow this down to 2 layers where there's no anti-ferromagnetism, and I put a little teeny field on, you can see that this looks like it extrapolates. But if I put a bigger field on, you can see this doesn't look like this has something to do with this extrapolation. So let's talk about the field dependence of this coefficient. So first of all, I want to go ahead a little bit. So here's the anti-ferromagnetism being suppressed by dimensionality. I'm not tuning it with doping, I'm not tuning it with pressure, I'm not tuning it with field, I'm tuning it with D, dimensionality. As I make the layers fewer and fewer between the lanthanum and indium-3, I suppress the 10.2 Kelvin anti-ferromagnetic transition down to T equals 0. And then I have 3 regimes in the resistivity. In this region, which keeps going upwards in temperature, I have non-Fermi liquid behavior. If I measure the resistivity sort of directly above the tuning parameter and not too far over, I can get non-Fermi liquid behavior. Now over here, as I run the tuning parameter or a tuning parameter higher, for instance, magnetic field, if I run the magnetic field higher, for instance, I go from 0 to 0.2 Tesla, that point right there. According to this, I can get Fermi-liquid behavior. So below a particular temperature, I can get Fermi-liquid behavior as I tune the field here. So that's what I'm claiming is happening here. As I move across by tuning, at low temperature, I can get T squared in the resistivity, and now I'll finally slow down and look at it. So here I have m equal 2, yep, here's m equal 2, and I have 4 interspacing layers of lanthanum instead of 3. So 2 of these and 4 of these, so they're nicely stretched apart. T-N-A-L is almost suppressed, and above T-N-A-L, in this phase diagram, I have non-Fermi liquid behavior. Again, this has been sized, this OR is over here, behavior. So I have a slope of n equal 1 in my resistivity for the m equal 2. And then at higher temperature, so I've tuned to here, at higher temperature I get to a crossover regime where I have neither simple t to the first nor simple, no, I don't have simple t squared, I don't have simple t to the 1, I have something in between. So here is at a tuning, this has been tuned by dimension. I'm at the non-Fermi liquid point from here up to here, and then it goes away to something else. So I didn't promise you non-Fermi liquid behavior forever, but here at this point I have non-Fermi liquid behavior above T-N-A-L, so above 0.2, I have non-Fermi liquid behavior, or a slope of 1, t to the 1 in the resistivity for quite a way. And what happens if I put on 6 Tesla is I can get T squared behavior to higher temperature, and if I put on 12 Tesla, I can get to even higher temperature. So again, if I go over here to 6 Tesla, I can get T squared for some region, and if I go over here to 12 Tesla, I can get T squared for some further region. And so that's what this is. Here is the little bit of field, where I got a little bit of T squared, and then it went away because in this diagram it goes over to the crossover regime. So here's Fermi liquid. I told you this was hard, especially since they keep going back and forth. But if I go to 6 Tesla, you can see I get T squared, or Fermi liquid behavior in the resistivity, all the way up to here, which is not all that huge. And if I put on 6 Tesla, you can see I get Fermi liquid behavior even higher in temperature. So that is defining what's happening here, right? So I get Fermi liquid behavior right at where T-N-A-L gets suppressed to 0. So what we've seen is that the temperature and the field dependencies of the transport properties provide support for the presence of a quantum phase transition at the vicinity of where the cerium indium-3 looks two-dimensional. And so we've tuned it not by doping, not by pressure, not by field, but we've tuned it by dimensionality. And it's a very powerful tool, particularly if you can make clean samples. And again, I'm trying to pull this all together so that you remember everything we've talked about, which is a lot. If you go back to the striped phase picture, which again, I didn't talk much about. I didn't talk about the non-Fermi liquid regime, and this has been shifted, it should be here. I didn't talk about the non-Fermi liquid behavior. Here's the pseudo-gap line. So here we have some transition. Who knows if it's second order? But if it has something to do with the second order phase transition, and you suppressed it to t equals 0, then maybe you had a quantum critical point. Again, this P should be after the C, so quantum critical point at this doping level. So it's very often the case, also in the iron-based superconductors, that when you have your superconducting dome, that you have some second order phase transition like anti-ferromagnetism in the iron base that's being suppressed, and the anti-ferromagnetic transition runs into the peak of the dome. Okay? So if you can tune your quantum critical point, you can also tune across your superconducting dome. So the point of the story is you learn something about quantum critical behavior. You've learned something about tuning with dimensionality, and I'm going to let you go early. Thank you very much. And of course, we have lots of time for questions. 8, 10, 12, 13. We have a 13. Last time we had 18. Next time we have 8. Okay. Yeah.
So the critical parameter that you tune across the criticality.
Oh,
This can be anything, right? So this might be doping.
it can't be something that suppresses the fluctuations. So for instance, it was originally stated by a competitor colleague of mine named Hilbert von Leuneisen that you couldn't tune to a quantum critical point using magnetic field because you destroy the fluctuations. You know, it's anti-ferromagnetic fluctuations, it's magnetic fluctuations that you're tuning when you suppress the anti-ferromagnetism. The fluctuations that are there have an anti-ferromagnetic magnetic character, and if you tune there with the field, von Leuneisen said, well, you'll suppress the fluctuations, you can't do it. We found a system where you could, which he then adopted and said, this was my idea the whole time. I hope this is being recorded. Hilbert, hello. So you can't tune it with anything. You have to be a little careful.
And how about the left-hand side?
Well, this is whatever an antiferromagnet is.
So you can still go there with any of those parameters, the tuning parameters.
Well, yeah, but you're not going to find anything terribly exciting. I mean, this is going to have a resistivity that looks pretty Fermi-liquid-like.
So those parameters can tune you all over the place.
Right. And the fun thing is, which no one has done thoroughly, would be to measure the crossover regime. And of course, this is a simplified cartoon. It's not quite like this. But you saw in some of our data where you had Fermi liquid, and then at higher temperature it rolled over to something else. So you come up here, you have Fermi liquid, and it rolls over to something else. It would be fun someday if you had a graduate student slave in a clean system to go figure this out once. No one's ever done it. This is a theorist diagram.
So no one knows what the second phase is. So this
well, no one really has an explicit answer for what it should be, because of course it's complicated physics. This is Fermi liquid simple. This is non-Fermi liquid hard, difficult, and matching those two up in a crossover regime would be tough. Because there's really, to be honest, there's no good theory for these. There's simple, this is the leading order term in the temperature dependence, but there's no analytic theory of the non-Fermi liquid behavior. Because of course, you're talking about something, correlations that are infinite in extent. That's hard to write a theory for. I mean, infinite in extent is a big region. But quantum critical physics is a very powerful tool in superconductivity. And if you can't figure out what causes the superconductivity, you can always fall back and say, it must be quantum criticality. Of course, sometimes the problem is, where is the quantum criticality from? A pseudo-gap transition is not a second order phase transition. I hope you all noticed me wave my hands and shuffle my feet when I talk about that. This is not a second order phase transition. This is, but it's nowhere near here. And so what happens a lot experimentally is you discover quantum criticality somewhere in the phase diagram, and the second order phase transition is far away. And so people then draw another axis coming out of the board and say there's something that's behaving out of the board that leads to this quantum critical behavior in another dimension. And it's typically some sort of magnetism in the next direction. So you saw in the cerium, iridium, indium 5, where we put on field and induced a magnetic transition that was still developing at 45 Tesla. So there, if you had a doping axis here, this axis coming out of the board would be field, and somewhere out at 48 Tesla would be a field-induced transition, and you can come back down claiming that the quantum criticality was in an orthogonal dimension.
So you still might not have the quantum criticality at t equals 0, even if it is if you destroy superconductivity at t equals 0, it's not quantum critical point.
Well, the people that study cuprate physics don't understand the superconductivity, so they drew this. I didn't put this here. I put the quantum critical point question mark, but you know, there are iron-based superconductors where anti-ferromagnetism comes nicely down to the top of the dome, and it's believed there's quantum critical behavior. But the problem is, it's like looking for the lower transition in uranium, thorium, beryllium-13. The fact that you have superconductivity up here buries your ability to measure the resistivity, because it's been shorted. Resistivity is equal to 0, it has no temperature dependence. So if you've got rho goes as T to the first power down here, there's no way to see it until you put a field on to suppress the superconductivity. And if you're talking about YBCO, that's 120 Tesla. Not technically available this week. One of the ways to make high magnetic fields, by the way, is to take an aluminum can and run a current in it, and then do flux compression. So in other words, you've got some flux, and then you squeeze it down to a much smaller dimension, and the flux that was in the bigger aluminum can then gets squeezed down, so the flux density is very high. And the way to do that, of course, is with plastic explosives. And so one of the ways the early YBCO people did high field studies, de Haaspenhofen, etc., was to go in the canyon in Los Alamos, put the sample in the middle of an aluminum sheath, put as big a current as they could get in it, and then light the explosives, and then get a very high magnetic field for a short time. And so they actually had a paper that they had submitted to PhysRev Letters, I'm telling stories, where they had seen a couple of de Haaspenhofen peaks at high field in YBCO, and it was a great discovery. Great, fantastic. And then the technician that was in charge of all of this stopped them pushing it, because he said, there was a little timing problem. The signal you measured came a few microseconds before the shock wave hit. So you were in zero field at the time. So, yeah, that's a difficult technique, but one way to get high magnetic fields is to do flux compression.
How much you can get in Teslas without using superconducting magnets, and without explosives, just coil and...
The pulsed field facility at Los Alamos has a 100 Tesla installation. The 100 Tesla is all normal state. There's no superconductivity involved at all, and it's more or less a traditional, well, it's an inner solenoid and an outer solenoid, but more or less it's a traditional wire-wound solenoid that's immersed in liquid nitrogen, and you put the energy in there for a short time so you don't melt your coil, right? So you can get a fairly flat top field versus time profile that's fairly flat at 100 Tesla for a millisecond. So if you can do your measurements in under a millisecond, you can go to 100 Tesla. Now this magnet has blown up once. It's very exciting. I've used it. I've measured specific heat in 100 Tesla. Very difficult, particularly if you're using a metal, because as you ramp the field up, you have all of these induced currents. Plus, there's something called the magnetocaloric effect. So this, if the specific heat of your sample changes with field, it will move to a different temperature because you've changed the field due to the magnetocaloric effect. So we discovered lots of things. But they make you exit the building when the field pulses, and the field only pulses once an hour because you have to cool the wire down so you can run all that energy. And you might ask, where does Los Alamos get such a large power supply? Well, it's a 1.4 megawatt power generator from some power project in Tennessee that was discovered to be surplus, declared to be surplus. And so they put it on these big trucks, built a new bridge actually between Tennessee and Los Alamos, and trucked it up the hill to Los Alamos, installed it. And what it is there's a flywheel in there, and so they draw energy out of the flywheel for a short time, and then, you know, they run it back up, and then they draw it down. And so they take about 40% of the energy out at a given time, but it's this, it has enough energy to go to much higher field, it's just the coil won't take it. And so one time, the wire in the coil broke, and the program in the magnetic power supply said, we know what the field looks like versus time. So as we ramp our current up, we will measure the field. And if the field deviates from what we know it should be, we'll change the current to make sure we're on path. So when the wire broke, the field ramp up wasn't going right. And so the program said, we must need more current, which of course melted and blew up everything because there was no place for the current to go. So they jammed the power in to where it couldn't go and just, I actually heard it. I was like 2.5 miles away. I actually heard the boom. It was exciting. So they've got the 100 Tesla up and running again, but worry about magnetocaloric effect and worry about metals, because anything that's pulsed has a whole lot of induced currents. So you can do a thin film where the film is such that the currents don't, you know, the currents don't induce in the film, they go perpendicular to the film, so that'll be fine. So if you have your field perpendicular to the film, you're in good shape. You go to 100 Tesla, metallic film, no problem. Well, with those questions, we've run out of time. So next time, just so everyone remembers that you have to come back, because of course, the next time, and again, this is really two-dimensional. So this wasn't so two-dimensional, sort of an introduction, but this is really two-dimensional, and this, of course, is the modern topics of what's going on today in high-temperature superconductivity. So these two should be somewhat more topical for people working in twisted bilayer graphene and iron selenide on strontium titanate. Thank you very much.